Question number 3, we need to complete this table with the symbol of the ion, number of protons, electrons, and neutrons, and you're getting 2 marks for that because you have to give this nuclide notation, or what I call the international standard notation. The mass number of the nucleon number is on the top left. You can include the proton number at the bottom left, and you have to have the correct sign for the charges there, as well as the element there. First of all, this proton number 15, so that means the atomic number is going to be 15. Element number 15 in the periodic table is phosphorus. We look at the mass number, not the relative atomic mass. The mass number is not relative atomic mass. They have different definitions in the syllabus. The mass number is going to be the proton number, number of protons, plus the number of neutrons. So you have 15 protons and you have 18 neutrons. So what do you get there? You're going to get 33 nucleon. So I'm going to get phosphorus 33, not 31 as 31 point something as stated in your periodic table, because you know that one is relative atomic mass. 33 there is the nucleon number there. And I have a charge. I have 1 extra electrons than protons. If you compare carefully, you have 1 extra electrons than protons. So that means your overall charge is just a -1 and not the usual 3 minus. So you need to be very careful and interpret information. That's what a year 9 student in IGCSE, GCSE or O-level chemistry should be able to do anyway to get these 2 marks in A-level chemistry paper. Question part B, this is about a fixed assay. This is solubility of the sulfate for group 2 element. This day they will no longer use the Roman numeral. They use the group 2 like this using the number. Solubility of the sulfate. So first of all, you need to describe the trend. So we know that the group 2 sulfate become less soluble than group 2. They become less soluble than group 2. This is straight from the AS trend. In AS chemistry, candidates are expected to be able to explain, well, not explain, but state the solubility of group 2 sulfate becoming less soluble and group 2 hydroxide becoming more soluble. Opposite trend there. What happened down group 2? Well, we need to think about solubility, so I better write down some hash cycle to show what I'm saying. So the group 2 sulfate, M2 plus and SO42 minus, will dissolve in water, in a large amount of water, to give you infinitely dilute solution. That is going to be the definition of enthalpy of solutions as stated in the A2 energetics syllabus. And what I get is I'm going to go via the lattice enthalpy. So it's the gaseous ion. So that is going to be the hydration of the cation. And then I have hydration of the anion. So there's hydration of the sulfate, SO42 minus. And what next on the left-hand side? I have the lattice enthalpy of the group 2 sulfate. So what I want really is to think about Hess law. Hess law says that the enthalpy change of these reactions is independent. It does not depend on which route I take, whether I take the direct route or whether I take the indirect route. As long as I start from the same reactant and end up with the same products, my enthalpy change will be the same. So what I can see from the relationship is that the delta H solution is equal to minus the lattice enthalpy, because I'm going against the definition of this thing, which is going upward. I'm going against it, so it's minus the lattice enthalpy there. Okay, and then I am going in the same direction, so there's hydration of the cation plus the hydration of the sulfate. Now that is just our expression there. It doesn't matter what that is, because now we're going to compare down group 2 what is actually happening. Down group 2, there are more filled electron shells. If there are more filled electron shells, so we can say the ionic radius of M2 plus cation will get bigger as there are more shells, but still +2 charge. If you still have the same +2 charge, we say charge density of cations decreases. So charge density of cations will decrease. And when the charge density of cation decrease, this will result in both the delta H lattice and also the hydration of the cations, they will become less exothermic as you are forming weaker ionic bonds. Due to the lower charge density of the cations, you're also forming weaker ion dipole bonds. As per the definition of hydration, you surround the ion with water molecule, which is polar ions, and the polar water molecule, they form ion dipole bonds. Naturally, they are exothermic. But as the charge density of cation decreases, both of these become less exothermic. So what do we want? We want the group 2 sulfate to become less soluble based on the trend we know. So that means the enthalpy of solutions will become more endothermic. More endothermic, therefore become less soluble. More endothermic means this is going to become more positive. So if you want this to be more positive, lattice enthalpy is defined in this direction. It will be negative sign, because you are forming 1 mole of the ionic solid from its gaseous ion. So the lattice is going to be negative in sign. Minus negative will give you positive. So positive sign there. And then the plus hydration is always going to be negative for the hydration. Multiplied by plus is a negative. So based on these equations and the definition is stated in the diagram here, this minus negative is going to be positive term. This plus negative is going to be negative term. You want the overall enthalpy of solution to become more endothermic because we know it becomes less soluble. So overall delta H solution is more endothermic, or you can think about it being less exothermic, but I'm just going to keep it simple and say more endothermic, so it becomes more positive in value. And this is because something is decreasing lesser than the other, or something is decreasing more than the other. You want it to become more positive, so it's more endothermic, so it's becoming more positive, because this value, which is positive, cannot decrease as much. So this value, which is negative, will decrease much more. So the decrease in hydration of the cation must be greater than the decrease in lattice, or you can say the decrease in lattice must be lesser than the decrease in hydration. Both way will mean the same thing. So that means the decrease in lattice is lesser than the decrease in hydration of the cation. So hydration could be cation or anion, but our anion is not changing as they are all sulfate. We're just changing the cations, and that affect the charge density of cations. Both lattice and hydration become less exothermic, but one of them decrease more than the other. If you want the overall to become more endothermic, for it to become less soluble as per the trend you know from AS, you need the minus negative, which is the positive term, to be bigger than this term, which is negative. For this term to be bigger, you do not want it to decrease more. You want it to decrease less compared to this term, or you want the hydration of a cation to decrease more than the decrease in lattice there. Hopefully that makes sense there, and that completes the 4 marks essay, including the trend there. Sometimes 4 marks, sometimes 5 marks. You really got to know the essay if you want to do well for solubility stuff and things you can prepare. The other one will be the opposite trend, which is solubility of the group 2 hydroxide. On to the next question. Calcium sulfate is sparingly soluble in water. So realistically speaking, we are talking about KSP, which is to do with solubility products. So not very soluble at all. What do we see? So if we have calcium sulfate, we will expect an equilibrium to be like this. So this is the KSP equilibrium. So it is an equilibrium. But what happened when I add a little bit of concentrated Na2SO4? You have known from O-level or GCSE chemistry or IGCSE, all sodium salts are soluble in water. All sodium salts are soluble in water. So I do not have an equilibrium. In fact, I have a fully dissociated equation there. So, what do I mean by this? When I add this thing to a saturated solution of these, so I started with solution of these. So I have a solution. But what's going to happen is you can see the SO4 minus and the SO4 minus there. So what happened is the Na2SO4 aqueous has a common ion. This is called the common ion. Has a common ion, which is the sulfate to that in the sparingly soluble salt. Actually, I don't want to talk about the common ion like that because it's just the name of an effect, and it doesn't mean anything if you can't really talk about what is happening. So I just state that it's common ion effect, but you gotta explain it. By stating common ion effect, you wouldn't get any marks, okay? So what we can say is the sulfate concentration from the Na2SO4 is going to increase due to Na2SO4 fully dissociated. And when that increase in the two component system, this is mixed together, right? You add this thing to this thing here. So what would the KSP equilibrium tries to do? You would try to decrease the concentration of SO4 minus, and then if you try to decrease the concentration of SO4 minus, the only way to do it is react more of it and go backward. So it will favor it will shift to the left hand side. Shift to the left side. And when you shift more to the left side, there is lesser of the aqueous ions, then you will get solid. So this is called precipitation. So therefore, the calcium sulfate solid will precipitate out, or it will start to form a suspension of solid. So this is called common ion effect. Describe what you see. You will see this precipitating out. And why do you see that? Because when you add this soluble salt to this mixture here, to these solutions that contain this saturated solutions, you're going to have so much more sulfate. Common ion to that is going to increase the concentration of the sulfate. Equilibrium tries to remove the sulfate, reacts more of the sulfate with the Ca2 plus, go backward, precipitate out the solid there. So it's all about what would the equilibrium do in response to what you just add to the system in equilibrium there. Common ion effect. In this part D, the last bit of this question, this is about electrolysis. So we have a half equation there. We do not know what is the charge there, N plus. We don't know the charge. If it is N plus, to get the chromium metal, you must get N number of electrons. We are given current and we are given time in minutes. So this is pretty much one of those Q equal to IT kind of question where the T has to be in second. Be very careful. 1 minute is 60 seconds. Your physics will have told you the time they must be in second. So Q is equal to 1.8 amperes times 40 times 60 to convert it to second. So put that into your calculator. 1.8 times 40 times 60. I get 4320 coulomb. And I deposited 0.776 gram of chromium. So I really need the relative atomic mass of chromium from the periodic table because we are dealing with reacting masses. Chromium, first row of transition metal, that is 52.0 there. And we have to involve the Faraday constant as well. So 96,500 coulomb per mole. In the 2022 papers onward, the data booklet will be given inside the question paper itself. So I cannot imagine that you can do this kind of question without being given the constant, either in front of the question paper, as part of the data booklet embedded inside the question paper, or even at the back of the question paper as the data booklet inside the question paper again. So what happened then is we can find the mole of chromium. So you can find the mole of chromium. You can relate that to the mole of electrons. Okay, and then you can find N because you want to find N there. So this is the actual charge that passed through. So what can I say about this? If I have Faraday constant, what does Faraday constant mean? Is per 1 mole of electrons. It is the charge for 1 mole of electrons. So if I have 96,500 coulomb, that is for 1 mole of electrons. If I have 4320 coulomb, how many mole of electrons do I have? That is the direct proportion question. So 4320 coulomb divided by 96,500 coulomb. What I get there is going to be, if I move that down there, so 4320 divided by 96,500, I get 0.04477. I'm just going to use it to 4 significant figure. I do not want to round it up to 3 yet because this thing was to 3 significant figure, 1, 2, and 3. The 0.776, 1, 2, and 3. This is 2 significant figure. This 2 significant figure. If I give 2 significant figure here, I will lose quite a great deal of accuracy going on later. So I just leave it to 4, and then I can probably leave it to 3 or 2 significant figure for my very last bit of the answer. But I doubt it because n has to be a whole number, so I will have to give n to whole number later on. So this is mole of electrons there, yeah? Once I have the mole of electrons, I need to look back at my half equation. I have the mole of electrons to be n. I have the mole of chromium, which is mass 0.776 divided by the AR. So I can say the mole of the electrons is to the mole of chromium. From the balance equation is n over 1. N number of mole of electrons is to 1 mole of chromium from the balance equation. This is equal to, on the top I've put the electrons there, so that is just the actual number of electrons, which is 0.04477, and at the bottom I must have the actual number of mole of chromium that I deposited in my electrolysis. 0.776 is mass divided by AR is your mole of chromium. So what is n then? Well, n is just going to be moving the 1 up there. It's just the whole thing multiplied by 1, which is itself again. So I just need to do 0.04477 divided by bracket. Divided by, what am I doing? I don't know what's wrong with my calculator. Okay, let's try that again. 0.004477 divided by bracket 0.776 divided by 52.0, close bracket. And I get quite a nice answer. I get a 3.0001. And this must be to the nearest whole number because it's the number of electrons. So looking at the equation, 3 electrons, chromium 3 plus 3 electrons, giving you chromium solid there. And that gives you the 4 marks by doing all sorts of calculations with the correct units, with the correct idea, labeling stuff so that it makes sense, so that it allows you to quickly understand and check your work there. And that's the end of that 12-mark questions there.